Hello and welcome to my channel. Today is the third episode in series of statistics. So, exploring statistics 3, statistical treatment of random errors. In the last episode, actually, we have discussed what is random error. Individually, the errors are very small and not even mostly identifiable or detectable, but the accumulated effect that gives some definite results, definite random errors of different probable numbers, and distribution, that particular error divided by the total number of errors, the accumulated errors, that is the relative frequency. And if we just plot this relative frequency, we will get a distribution. And we have also discussed a very popular, famous and popular distribution called normal or Gaussian distribution. And more importantly, we have seen a connection between the random error distribution, as I have mentioned, and the Gaussian distribution. And actually, we have seen that connection is so fundamental and intimate that we can safely start with an assumption in today's discussion. The assumption is random errors in analytical results follow a Gaussian or normal distribution. So, if we understand the normal distribution or Gaussian distribution, then it would be easier for us to follow the rest of the study. And one more point was discussed, that sample versus population, as if a sample is the subset of a population, which is a set. Sample is much smaller in size. This is for our convenience, because mostly we cannot handle the whole population, so much of data would be there. So we make analysis and study on sample, but we want to infer on the population on the basis of the sample study. And so it's an important question that sample, if it contains only a few points, it really doesn't represent the whole population. So the number of points in the sample is important. And moreover, whatever the laws we have derived, that are actually derived for population, but we want to apply them for sample and then infer on the population. So we need to modify the formula and the laws from population to sample, so that we can apply them for sample, right? And this is the Gaussian distribution mathematical expression. As you see that there are two parameters, sigma and mu. X is the variable. So mu is the mean, average, and standard deviation is sigma. Okay, these are the two names of these two variables. We will see what do they mean. And the mu is actually supposed to be the true value for the measured quantity, if it is the population mean. And mostly we don't know that. So what we will do, we'll start with a sample and take its average, and from there we want to get mu, that's population average, right? How do you do that? Well, the definition is simple. X average is sum of our x values divided by n. N is the number of measurements of the sample, and exactly the same expression, but here n is the total number of measurements of the whole population, which is obviously very big. And intuitively we can say that if you take really n very large, then this x average tends to mu, as n tends to very large. That's okay. Now we will start with Gaussian for population first, then we will go for sample. The population standard deviation sigma, which is a measure of the precision of the population actually, and is given by the equation like xi minus mu square summation divided by n and the square root of the whole. So we will not discuss the mathematical rationale, or rather you can say the mathematical philosophy behind this definition or expression of sigma. This is the formula, and we will be seeing the important significance and how we can apply the sigma for analysis. So this is the formula, where n is obviously the number of data points making up the population, and this looks like this curve. And as you see, a few salient features here. This sigma somehow is connected to the width or breadth of this curve, right? More the sigma value, more flat the curve is, right? More wide it is. So the sigma features are like symmetric around the mean. So it's a highly symmetric curve, and is apparent from the expression as well. And the mean here, the mean is at the midpoint, right? And at the midpoint, that is here, the relative frequency is maximum, and on both sides of the maximum, it is an exponential decay, right? So these are the features of the Gaussian curve. Now, for our convenience, as you understand that if the sigma values are different, then you are going to get different Gaussian curves. But for our convenience, if we want a single only curve, irrespective of the sigma values, then what we can do? You can remember the reduced equation of state in kinetic theory in this chapter. That reduced equation of state. There is a variable transformation, and here we are going to do the same. We transform x to z, and how do we define z? X minus mu by sigma. That means it is a deviation from the mean, but relative to 1 sigma, that is divided by sigma. And here the advantage is that, for z equal to 1, if z equal to 1, then x minus mu is sigma. If z equal to 2, then x minus mu is 2 sigma, and so on. The advantage is that relative frequency versus z, not x. If we plot, then it is the same irrespective of the standard deviations of the Gaussian curves. I will show by an example. And if you really transform the equation from variable from x to z, then the equation also transforms like this. So in place of x, it is z, and this is the final form. One can easily check it by transform. And this sigma square is important factor. Sigma is standard deviation, and sigma square is called variance, right? Variance. So here, this example, there are two Gaussian curves shown here, A and B. Obviously, B is more flat. That means the sigma value is here twice that of the sigma of A, right? So we are getting two curves. And if we plot against x minus mu in the units of measurement, right, in simple unit. But if we measure in the unit of sigma, and well, the next graph, if you plot not against x minus mu but against z, where z is x minus mu by sigma. So here it is in the unit of sigma, right? And then we get the same single curve for both A and B. That is the advantage. A single curve is enough. Well, this is the z and x relation. This is the Gaussian distribution in x. This is the distribution in terms of z. And here is the plot. And here I have shaded an area, color set, area. How one can calculate the area and what does it signify? This is very important in analytical chemistry. How we can calculate? It is a question of the calculus, application of calculus. If you integrate over a range, say minus sigma to plus sigma, that means what is the area under the curve in the limit of minus sigma to plus sigma? You have to just integrate the function over x dx. Okay, and we are using z, so if you again transform the variable, then it becomes an equivalent problem of integration of this function over z. and the limit is -1 to +1, not minus sigma to plus sigma. Of course, this integral is has no closed form solution, so you have to integrate it over using the numerical method by using a computer, and the area comes out to be 0.683. Fine. So the area of the shaded area is -1 to +1 in this unit is 0.683. Now, what does it mean? Well, first of all, 68.3%, and important is regardless of its weight, 68.3% lies within one standard deviation, plus minus 1 of the mean, right? So plus minus 1 sigma. And another meaning, that means 1 sigma on either side of the mean. Another meaning is that more understandable, that chances are 68.3 in 100 that the random uncertainty of any single measurement is no more than plus minus 1. So I repeat, the chances are 68.3 in 100 that the random uncertainty of any single measurement is no more than plus minus. So if you do different experiment measurement, you will get different values, but the uncertainty would be maximum within plus minus 1. That is the guarantee that this analysis gives, right? So if you want to increase the percentage, of course the range should be more than 1 plus minus 1. Say for example, if I am interested in plus minus 2, then the area increases 0.954, right? So chances is 95.4 in 100 that the uncertainty of any single measurement would be within plus minus 2 sigma. So it's a rather wider range. Similarly, if I want plus minus 3 sigma, the area is even bigger, minus 0.997, and this is the curve looks like that. And finally, as you know that it's a probability distribution, so the total probability area under the whole curve over the whole range limit, it should be 1. So if you integrate from minus infinity to plus infinity, it should give you 1. Okay. Now let us quickly see a tricky problem. From the Gaussian error curve, what is the probability that a result from a population lies between 0 and 1 sigma? So far we have seen minus to plus 1 sigma. Now it is asking between 0 and 1 sigma. What is the probability, second question, of a result occurring that is between 1 sigma to 2 sigma of the mean? So how I can answer the question? If you know that the probability is what it is between minus to plus, and since the graph is symmetrical, then 0 to 1 and 0 to minus 1, these two probabilities will be same symmetry. So that means the probability between minus 1 to plus 1 is 0.683. So it is just half of that between 0 to plus sigma. So it is half of the value of 683, that is 0.34. And the next part of the question, what's the probability between 1 sigma and 2 sigma? So suppose you know that plus minus 2 sigma, right, 0.954, and plus minus 1 sigma, 0.68. So if you take the difference, what you will get? Because it is symmetrical, finally you can make it half. So 0 to 2 minus 0 to 1, that gives you 1 to 2. I repeat, 0 to 2, which is half of the minus 2 to plus 2, and 0 to 1, which is half of the minus 1 to plus 1, right? So if you take the difference, that would give you from plus 1 to plus 2 sigma of the, right? So you just take the difference of these two values, plus minus 2 sigma and plus minus 1 sigma, and take the half, and you will get the result 0.136. Another problem, from the normal curve of error, find the probability that a result is outside the limit of plus minus 2 sigma from the mean. What is the probability that a result has a more negative deviation from the mean than minus 2 sigma? So there are two questions. The first part is what is outside. So as you know, the total probability is 1, and between plus minus 2 sigma is 0.954, etc. So 1 minus this value, that would give you what is the probability outside the plus minus 2 sigma range, right? So the answer is very simple, that you just take 1 minus 0.954, that would give you the probability outside plus minus 2 sigma range. So the next part is outside means it is within greater than 2 sigma to infinity, and it is within minus less than minus 2 sigma to minus infinity, right? And the graph is symmetric. So just greater than or less than, they would be same, and that's why the answer finally is half of the value that you get, 0.046, half of the value 0.02, right? Okay. Now we come to the point sample standard deviation. So far we have studied population standard deviation. Again, it's a measure of precision, and for a small sample of data, the sample standard deviation is, instead of sigma we call it S, is modified. So we mentioned in the very first slide that we need to modify the equation from population to sample. So here we are going to get S from sigma, right? How we can do that? So this is the equation, again without explaining the rationale or philosophy of the equation. One thing just to note, that mu in the earlier formula, here it was mu population mean, it is replaced by x bar, that means the sample mean. And another thing is that n, it was n there, but now it is n minus 1. We call it degree of freedom, n minus 1. Well, I'm coming in a while what is degree of freedom. And similarly, like sigma square, here S square is called the variance. Well, this is just an alternative formula for the same definition. Yes, we'll be using that, and so that the same result we get. And what about number of degrees of freedom, right? So by definition, it is something that indicates the number of independent results that enter into the computation of this. Number of independent. So you are using n number of data, but all n number of data are not important or independent. You can just avoid just a single value. It is like that. If you know the average x bar, then how many you need actually the x component? 1, 2, 3 up to n minus 1, because the last one is automatic, because you know the x bar, and it is more like the mole fraction. Total mole fraction is unity, so you need actually the n minus 1 components mole fraction, and then last one is automatic. So it is this kind of thing, degrees of freedom. Now let us see quickly an example. The following results were obtained in the replicate determination of the lead content of a blood sample, 0.752, 0.756, 752, etc. ppm of lead. Now find the mean and the standard deviation of the set of data. So we are going to straightforwardly use the formula. And what is the formula that we know? So for the formula, we need to evaluate the sum of xi. This is the sum of xi, and this is the sum of xi square. Okay, because the formula needs that. So one is needed is the sum of squares. Sum of squares. That means this one, and other is square of sum. Right, square of sum. So the sum is here, and we'll make it squared. Okay, to get this two. And n is known, so n minus 1 is also known. So we can now apply. So x average, the mean, first one, is simply this sum of xi by n. So this is the first one. Now for the second part, square of sum and sum of square. So this is the square of sum, right, and divided by n. So this term, and that gives you this value. And the sum of squares, that is here, so we are using here, and finally the degree of freedom is 5 minus 1. Why 5 minus 1? Because you are using 1, 2, 3, 4, 5 sets, and so minus 1. 5 minus 1 is 4. Okay. And one word of caution here, I must mention that you see the result is very small in magnitude. So if you try to round off the data in every step of your calculation, that is going to definitely going to give you a wrong result. So my word of caution is that never round until the end. Okay. And one more point, that this equation is better, convenient, more convenient for digits more greater than 5 digits. Okay. And of course, this x average and this s, which is sample average and sample standard deviation, are estimators, better estimators of mu and sigma respectively, if provided large n. N is large. Okay. Standard error of the mean. So I am reading out this passage. The probability figures for the Gaussian distribution calculated as areas refer to the probable error for a single measure. Thus, it is 95.4% probable that a single result from a probability will be within plus minus 2 sigma, as we have already seen. If a series of replicate results, each containing n measurements, are taken randomly from a population of results, the mean of each set will show less and less scatter as n. That means instead of single measurement, if you are not happy enough with single measurement, then you can go for n measurement. And then, okay, if you are even then not happy, then you go for another n measurement. So, or n prime measurement. So, as you increase the n, the curve would be less scattered. Okay, sigma would be lesser. The standard deviation of each mean is known as the standard error of the mean. So, we are defining a new term. It is nothing but s by just root n. Okay, and which we call SM, standard error of the mean. That would be more relevant in our next episode actually. Now, reliability of S as a measure of precision. How reliable that we are calculating for the sample? Usually, it's an experience that if you take n to be greater than equal to 20, then S is usually a good estimator of sigma. It's our experience. For example, we are measuring some volume and we are getting different range, right? 9.969 to 971, 3 such values we have got in this range, 7 values we have got in this range, and so on. The total number of times we have measured is 50, and percentage in range, that is 3 in 50, 1 in 50, and so on, that is percentage, and of course the total percentage is 100%. So with this much of data, let us see. Now let us divide 50 measurements into 10 subgroups of 5 each. So that n1 number, n2 number, n3 number. So these results are divided into 10 subgroups of 5 each, and we can calculate for each subgroup the S using formula, and we see that the S values vary widely for 10 subgroups. It is from as low as 0.0023 to as high as 0.0079. It's quite a long range, because we have taken different subsets, but of only 5 members of each, right? Now, let us think of that we are dividing these 50 measurements into 2 subgroups only of 25. So, the number is big enough, 25 instead of 5. And here we see the S values are nearly identical. It ranges from only 0.054 to 0.058. So, the range is very small. But even then, you may not be happy. You may be confused that, well, which one I will take, 0.054 or 0.058 or the average of this or something else. That means how we can make it even improved, more improved, this S value, which would come out of these 2 values. Or in other words, if I can club together or pull together these 2 subgroup results, that is the next slide. Pooling data to improve the reliability of S. So we call it pooling data. So you can take so many sets actually. Suppose n1 number of sets, n1 number of members in the first set, n2 number in the second set, and so on. And this is the formula for S pooled. So what we do actually, deviations from the mean for each subset. So xi minus x1, the first set, x1, and then squared, it is squared, and then sum. So this part, sum for the first set and second set. So this summation is talking about the sum, first, second, third, and so on. And then you divide by the number of degrees of freedom, and finally you are taking the square to get the S pool, right? So degrees of freedom here, 1 degree of freedom is lost for each subset, as we have seen that n minus 1 for the first one, n minus 1 for second, and so on. Of course, the n values may be different. Now, if it is 1 for each subset, and how many subsets are there, you have to count, and that number of 1 would be subtracted from the total number of measurements, right? So the degrees of freedom is equal to number of measurements minus number of subsets. So it would be even more clear after the example. So, the example are glucose levels are routinely monitored in patients suffering from diabetes. The glucose concentrations in a patient with mildly elevated glucose levels were determined in different months by a spectrophotometric analytical method. The patient was placed in a low sugar diet to reduce the glucose levels. The following results are obtained during a study to determine the effectiveness of the diet. Calculate a pooled estimate of the standard deviation of the method. Why pooled? Because we have taken results of different months. So the month 1 results you can call the first set. Similarly, month 2, month 3, and month 4. So we have got actually 4 sets of data, right, for 4 months. And you can take the mean of this each set. The means are like this, and sum of squares of deviations from mean, that I will show in the next slide how we calculate that. Then we finally apply the formula to get the standard deviation. So let me check. So here the table again, and xi minus x1 average 12. So x1, the first set, averages 1100 points. Okay. So what we do? We take 1108 minus this mean value and square, right? And then 1122 minus this mean value and then square, and then the next value minus mean square, next value minus mean square, and summation. So this is the way how we get 1687.4 this value. So by similar approach we get for the other months or other subsets. So these are the values. Okay. Now you can calculate the final result, and the total sum of squares, if you just add all these 4 values, you will get 6907.89. And how many measurements? If you just count that how many measurements you have done in all 4 months, it is actually 24. You can count 24. So what is the final formula? That S pooled is this sum of squares divided by BOF, degree of freedom, and the degree of freedom is total number of measurements minus the total number of subsets. How many? 4 months. So the result is 19 unit. And you see for individual set the range is from as low as 16.8 to as high as 22.2. So you are a bit quite confused that which one is the correct or more correct, and it is supposed to be the more accurate one, this S pooled 19. Okay. Finally, variance and other measures of precision. So although the sample standard deviation is usually used in reporting the precision of analytical data, but that requires a lot of calculation. So often for simpler cases we find the other terms, and what are they? The first one is variance, as we have already mentioned, S square for sample. The variance is nothing but the square of the standard deviation. So it is very simple. The definition of standard deviation is here, and if we just eliminate the square root, then you get the standard deviation. you get the variance. And the next term is RSD, relative standard deviation, and another one is coefficient of variation, CV. So what are this? Very simple. RSD is nothing but S divided by X bar, right? And if you take the percentage, that is, if you multiply RSD by 100, then you get what actually called the coefficient of variation, CV. So CV is RSD in percent, that is S by X bar into 100, right? And finally, the spread of range, and that is very simple, the difference between the largest value and the smallest value in the data set. So let us quickly see an example to explore this concepts. For the above set of data, let content problem that I have already shown, calculate 4 points: the variance, the RSD in PPT, that is parts per thousand, that means we have to multiply by 1000, the CV, that means we have to multiply by 100, and finally the spread. So the first one, X averages, suppose you know, and standard deviation you know of the sample. So variance is just square of this. So this is the answer. RSD is S by X average. So S is given, X average is given. So that is this by that into 1000. So RSD for PP10 PPT, right? And CV is the same ratio into 100 this time, and that gives you 0.5%, 0.50%, and the range is the highest and the smallest difference. So in this data set, the 0.760 is the highest one and the lowest one is 0.751. So the difference is between these two, and that gives you 0.009 ppm. Yeah. So these are the other terms that we sometimes use for indicating the accuracy, etc., precision. So thanks for watching. Our next video, exploring statistics 4, and that would cover applications of statistical data treatment, confidence interval, etc., which is very important. So in the next episode, we'll be applying some of the knowledge that we have already acquired in the last 3 episodes, and it will be coming soon. So please keep on watching. Till then, do subscribe and encourage your friends to subscribe. Thank you very much once again. Thank you.